In the manufacture of Brunswick tires, each cord is drawn from its individual spool. Guided by thousands of tiny eyelets, the cords are carried through a specially conditioned room where the temperature and moisture are strictly maintained to preserve full strength and elasticity of the cords. The manufacture and processing of the insulated cord construction is far more costly than the processing of ordinary pick fabric. Here, each cord must be held in positive position until it passes through huge calendars and formed into a wide sheet of ply stock containing 1,800 cords, thoroughly and evenly coated with a special rubber compound. The rubber used for this ply stock is so compounded that it possesses high anti-friction properties, which give further protection against internal friction and wear. The angle of the cords in the ply stock is an important factor in the life of the tire, because a definite angle is necessary to give proper balance to the body plies. In order to assure the correct angle and exact width of the plies, this enormous cutting machine is used. Accurate to a fraction of an inch, the strips are carried to the tire room individually on an immense system of conveyors. Another important part of a tire is the bead. The wire used has a breaking strength of 280,000 pounds per square inch. Each strand is thoroughly insulated with a special rubber compound, then automatically formed into a circular band. The spliced ends are taped, and on another machine are covered with a special rubberized fabric. This fabric covering is called the flipper. It's used to anchor the bead to the body of the tire. Another long, safe mileage feature of Brunswick tires is its famous safe and efficient tread. In order to produce this tough, wear-resisting tread stock, 7 different ingredients are blended in with the highest grade of raw rubber obtainable. Each ingredient is accurately weighed before it is mixed in the huge Banbury mixing machines. These machines mix 800 pounds at a time and then dump the batch to a conveyor belt which carries it to a series of large cylindrical rolls called mills for further mixing with additional compounds. These mills not only mix the rubber but knead it as well, much as bread dough is kneaded before baking. Another mill heats and prepares the stock, cutting it into a large, thick, continuous ribbon before it is fed into a machine which forms it into proper shape in width and thickness. Here it begins to look something like a tire tread as it travels along a 300-foot conveyor to be cooled, weighed, and checked. A special compound of adhesion gum is next applied and thoroughly rolled onto the underside of the raw tread strip. This layer later becomes a part of the double shock absorber unit, which provides the positive adhesion between the tread and the carcass. At the end of this long conveyor is an automatic cutting machine, which measures out and cuts the tread stock into the exact length required for different sized tires. Further check, however, is made on the weight of each strip of tread stock to assure proper balance to the tire. If the weight is off a fraction of an ounce, the strip is rejected. In the tire building room, the components are assembled. Plies, beads, flippers, tread stock, finishing strips, and double shock absorber units made ready for tire builders. Skillful operators with years of training and with equipment of the most modern type. This cylindrically shaped machine is called a drum. Each ply is rolled accurately and smoothly into place, one ply at a time. A system of rollers shape the plies to the drum and press out all air pockets between the plies in order to produce positive union of all parts of each ply. After the second ply is rolled down, the beads are placed on each side. The flipper strips surrounding the beads are securely fastened to the edges of this second ply, and the edges of the body fabric are lapped over the beads, locking them firmly into the body of the tire. The additional plies of cord fabric are then added one by one until the carcass is completely built up and prepared for the tread stock. One of the most common causes of premature tire failures and blowouts is the separation of the carcass and the tread. In order to eliminate this hazard, Brunswick has developed the double shock absorber unit. That's the center unit being applied. It consists of 2 extra layers of cord material treated and coated with a special cushion compound, which not only ensures positive adhesion of carcass and tread, but also protects the body of the tire from high-speed road shocks by absorbing and distributing them over a wide area of carcass. Double shock absorber is an exclusive Brunswick feature and found only in Brunswick Super Service tires. The 2 black strips at the sides are chafing strips. They protect the lower sidewalls of the tire from rim chafing and keep the flexing action of the sidewalls evenly distributed above the point of rim contact. The thick, tough tread stock is next placed smoothly and evenly over the entire carcass, the ends spliced securely together. It is rolled firmly and pressed to the carcass by the rollers at the bottom of the drum. When it's removed from the building drum, it's in the form of a hollow cylinder. It doesn't actually look like a tire until it's shaped in the forming box. Now here the tire is prepared for the mold. A heavy rubber tube called a water bag is placed inside the assembled tire in the forming box. A quick application of heat, and the tire is shaped to fit the curing molds. In the curing of a tire, heat and pressure should be applied uniformly to the inside as well as the outside of the tire. Otherwise, the rubber coating of the inner plies would be of a different consistency than the rubber of the outer plies. With the Brunswick hydro curing process, the tire receives a thorough, even cure throughout. Because after the tire is placed into the mold and the top half of the mold clamped down, it's lowered into a huge boiler or vulcanizer, and a fitting is attached to the water bag inside the tire. 28 molds are placed in each vulcanizer, each mold fitted with a water connection. A hydraulic ram gradually lowers the molds as they're placed. The water fittings interlock, forming a pipeline. When the vulcanizer is closed, water at a temperature of 300 degrees Fahrenheit and at a pressure of 240 pounds to the square inch is forced in the water bags inside the tires. At the same time, steam temperature of 300 degrees Fahrenheit is applied to the outside of the molds in the vulcanizer. The temperature and pressure of the water in the water bags, the steam in the vulcanizer, the hydraulic pressure on the ram, and the curing time are all accurately controlled from one central point by automatic regulation. The slow baking process gives an even cure throughout the tire and induces full adhesion of carcass and tread, not obtained where air is used in the bag, and the curing is done from the outside of the molds alone. As soon as the tires are cured, they're cooled by flushing the molds with cold water to prevent any possibility of over-curing. Removed from the vulcanizers to a long conveyor system. The molds are cracked open and the tires removed. In the finishing room, they're sprayed with tire paint, trademarked, striped, and balanced, then put through a rigid inspection test. In spite of the thoroughness, the constant check during each phase of manufacture, every tire is thoroughly inspected inside and out. No blemish or imperfection is overlooked. Every tire must check with the exacting specification set for it. Specification set by one of the most outstanding groups of research engineers and chemists in the industry. In the research laboratory, there's a constant quest for the better than best. Day after day, the search for new developments and product innovations is diligently carried on. Anticipating the needs of tomorrow, new formulas, new compounds are developed in a miniature factory. Toy-like in comparison to the huge equipment of the plant, but exact in detail are the Banbury mixing machines, mills, calendars, and vulcanizers. Here, small experimental batches of rubber are carefully compounded, mixed in miniature mills, rolled into sheets on small calendars, and cured in tiny ovens. Samples of these cured sheets of rubber compound are tested for their strength, stretch, elasticity, and resistance to wear. Every new compound is also tested for flexibility and its resistance to heat, set up by friction. Ply stock is experimented with and studied just as thoroughly. each component part receives its share of attention. Samples of cord are weighed and flexed on specially constructed devices both before and after they're conditioned in experimental ovens. Stretch and breaking points of cords are constantly being checked and charted on tensile strength machines. This laboratory checks not only experimental materials, but samples of all raw materials used in production as well. Sections of carcass and tread welded together or vulcanized by various experimental methods and compounds are flexed and tormented by specially designed flexing machines to determine their adhesive properties. Other tensile strength machines are used for a pull test to measure the number of pounds necessary to tear the tread from the carcass. This test proves the positive adhesion attained in Brunswick Super Service tires by the double shock absorber unit, not only on a cold pull test, but on heat tests as well. There's a section of the laboratory known as the torture chamber. It's aptly named because a tire that will run this gauntlet of tire-destructing mechanisms and survive truly earns its right to be called one of the finest tires ever built. Here is a Brunswick Super Service inflated to a pressure 4, 5, 6 times its regular inflation point. Pressure is forced into it until it bursts. The men conducting these tests are protected by heavily insulated partitions. Pound by pound, water is forced into the tube under pressure, inflating the tire to 200 pounds or more until something must give. Under this terrific pressure, the steel bead snapped, but the tire itself did not blow out. Another device is used to test the possible injury to a tire as a result of hitting into curbs or road obstructions. A tire is mounted on a heavily weighted steel rim and dropped on an iron cleat. This is repeated many times with the tire at many degrees of underinflation in an effort to penetrate the protecting wall of the double shock absorbing unit. On the Sprague machine, the ordinary tire doesn't last very long, because here is a test that compares only with the continuous run at incredibly high speeds over the roughest possible roads for thousands of miles without a stop. The tires are forced against a large dynamometer wheel at carload weights. The rough surface provides traction for the tires, which pull against the dynamometer load. Heavy iron cleats fastened to the large wheel pound the tire incessantly throughout the run. For the equivalent of thousands of miles, these tires are driven on and on for days at a time. Imagine the heat generated in the tires with an incessant pounding of the cleats, and every part of the tire pounding and flexing about 2,000 times a minute. The heat of the run expands the air inside the tire, forcing even greater pressure against the dynamometer wheel. Under these conditions, an ordinary tire soon fails, but the Brunswick Super Service, when put to this test, proves definitely its resistance to destructive high-speed flexing by running continuously for the equivalent of 10,000 miles without failure. Comparative tests are made against competitive tires to determine the degree of heat set up inside the tires when run on the Sprague machine. Thermal couplings are used to measure the internal heat set up under varying degrees of speed and load pressure. And tires that are built with pick fabric plies show a much higher temperature under the tread than the Brunswick Super Service, with its insulated cord construction. Even when run in heat rooms, where the temperature is kept at 115 degrees, Brunswick Super Service tires have passed the Sprague test with no sign of failure. But the most dramatic test of all is the pile driver. Here, a heavily weighted steel wedge is suspended over the tire. Guided by smoothly polished and greased runners, it's drawn up a tall shaft to a height of 90 feet. And that's the height of a 7-story building. When this steel wedge reaches the top, it's released. And gathering tremendous velocity in its downward plunge, this destructive force strikes the tire with terrific impact, sometimes rebounding 30 feet or more. No ordinary tire can possibly withstand this pile driver test. After each test in the torture chamber, the tires are sent to the dissection room of the laboratory. The tires are cut down, ply by ply, and studied for possible signs of injury or failure. If a tire fails, the cause of failure is immediately determined. But the final test of a tire is on the road. Under actual operating conditions, Brunswick is one of the few companies in the industry that maintains a large fleet of test cars and trucks. This test fleet proves conclusively the long, safe mileage built into Brunswick tires. Day after day, week after week, Brunswick tires are subjected to every condition of road surface and speed, over smooth highways, uphill and down, over rough roads and bumps that few drivers ever encounter. Accurate records of mileage and speeds are diligently kept. The tires are shifted and rotated around each wheel every 300 miles so that wear conditions are uniform. Now, these tests are continuous, with time out only for refueling or a change of drivers, running 24 hours a day, carrying on through the night in all kinds of weather. These tests are ultimate proof of the performance, quality, and safety of Brunswick Super Service tires.